So far in our study, if you have been following all the modules in a linear fashion, you will see that we have been studying things which are not dependent on time. We started with charge configuration that was essentially static, right? And then we talked about the electrostatic field that would arise out of this. Electrostatic would mean that the electric field is independent of time. There is no time variation anywhere, right? And when we let the charges move to form the currents, currents can only be formed when you have a charge movement, and charge movement would mean that there is some time variation involved in the charge configuration. However, as long as the current was steady, right, we did not have to worry too much, right, because the magnetostatic fields that were generated, they were all again independent of time. So this is the reason why we call both electrostatic fields and magnetostatic fields as static fields. Okay, these are static in the sense that there is nothing interesting is happening in terms of time. The moment you start varying the current going through a circuit, then very interesting things will begin to happen, and to understand that we need to introduce time dependency to our expressions, and we do that by discussing first what is perhaps the most important experimental discovery in the 19th century called Faraday's law, upon which the entire edifice of electromagnetics is built. And once we discuss that, we are in a position to understand what happens when time varying fields are present. Okay, so we will begin by discussing Faraday's law, which gives us the link between electric and magnetic fields, and then we will discuss some applications of Faraday's law and tell you what exactly this Faraday's law is useful for. And finally we will talk about a different form of link between magnetic field and electric field that cannot actually be related from just Faraday's law, but it can be understood in a broader sense of Faraday's law. Okay, so we will begin by considering what happens when you have a current that is carried by a particular loop. Okay, so we have a current. Let's assume that we actually have a loop. Okay, so we draw a loop here. And this loop is carrying a current I. Okay, or let's assume that initially the current loop is not carrying any current I. That would make Faraday's law very interesting. Okay, now if the loop is not carrying any current I, and we will assume that this gap that we have is very small, so we can consider this entire loop as a proper loop, closed loop. Okay, if this loop is carrying no current, then what happens? There is no magnetic field that is generated. But is it possible that if I have this loop and then I have a magnet, okay, nearby, so I have a magnet which is giving out magnetic fields everywhere, right? So these are the fields of the magnet, and if this magnet is there and there is a loop that is sitting here, what will there be any current in the loop? See, we know Ampere's law states that when there is a current carried in a conductor, there will be a magnetic field that is generated. We have seen the applications of this Ampere's law all along in the last few modules. Now we turn around and ask this question: if I have a loop and if a loop is subjected to a magnetic field, external magnetic field, will there be a current in the loop? It turns out that two people worked on this problem. Actually many people worked, but two of them were very famous, and both almost simultaneously got the correct answer. The correct answer being, yes, there will be a current in the loop provided the magnetic field is changing with time. Okay, if we take this loop and if we take this magnet and introduce the loop, okay, and both of them are constant with respect to each other, that is they are not varying with their positions, then there will be no current induced. Okay, when will current be induced? You keep the magnet where it is and then take the loop in and out, or you keep the loop where it is and then take the magnet and push it back and forth. When you are doing this, then the magnetic field that is associated with, or the magnetic field that is linking with the loop changes, and this change in the loop or change in the flux linking with the loop will induce a current. Okay, so this is what essentially two people, Faraday and Henry, found out. Henry was US and Faraday was English, but it so happened that Faraday was the first one to publish widely his findings, and therefore all these laws and the subsequent development is is given credit to Faraday. Okay. Henry is honored by giving the units for inductance, while Faraday has been a very influential scientist on Maxwell, who finally unified all of the electromagnetics. Okay. So, to reiterate what we were discussing, yes, it is possible for the loop to get induced by a current, okay, whenever there is an external magnetic field linking to the loop changes. This is very important. The magnetic field linking or the magnetic flux linking must change. Okay. So, when that happens, there will be a current induced in the loop, and what should be the direction of the current induced in the loop? Would it be along clockwise direction or would it be along the anti-clockwise direction? Well, the answer to that is conveniently comes from what is called as Lenz's law, and this Lenz law states that the induced current would generate a magnetic field which would oppose the original magnetic field. So, if it opposes, in the sense that if it subtracts from the original magnetic field, then the amount of this one that would be induced would actually be lessened. Now, when current is flowing through a conducting wire, right, it would actually give rise to a certain electromotive force, or in our words EMF or potential. Okay. In fact, Faraday's law does not really talk about current getting induced, but rather what he says, or what the law states, is that there is a EMF produced in the coil whenever there is a time rate of change of magnetic flux. Okay. If the magnetic flux is changing with time, then there is an EMF induced. EMF is called electromotive force, and this was sort of the force that people considered which was responsible for the movement of current. Okay. So, it is not really the current that we are actually inducing, although which is what happens, but it is more importantly the EMF that we are focused on. So, there is an EMF induced whenever the magnetic flux linking to that circuit is changing. Now, why is there a minus sign here? The minus sign is precisely Lenz's law. Minus sign is put so as to make us remember that the currents must be induced in such a way that the EMF actually reduces, right. The net flux change will be reduced. So, if you choose a current direction in one sense, the EMF could actually, or the current would generate its own magnetic field which would add to the original magnetic field, which means that the EMF would increase, right. However, you can actually do this in a continuous loop kind of a thing, right. So, you have a magnetic field, induced current gives you the induced EMF, and the induced current will generate a magnetic field which will add to the original magnetic field, increase the EMF, add more magnetic field, and this process can go on, which obviously will not happen in nature. What actually happens is the current induced in the coil would actually be in a direction that would reduce the magnetic flux linking to the circuit. Okay. So, in mathematical terms, this is all that is there for Faraday's law. Okay. There is an EMF induced in a coil or a circuit which is related to minus time rate of magnetic flux linking the coil. That is what Faraday's law states. To put it into slightly better form for us to understand, we express magnetic flux in terms of the magnetic field itself, or magnetic flux density B, right. What is the magnetic flux linking to a particular circuit? This would be equal to integral of B dot ds. This is something that we saw when we discussed inductance as well. So, there is a magnetic flux linking to a circuit, and that would be given by B dot ds, right. So, you can substitute for that. So, there is d by dt of magnetic field, and that would be getting converted into del by del t of B dot ds. Okay. I have chosen to take this d by dt inside into this B, assuming that whatever the surface I am integrating would remain constant. Okay. So, this is the case where the surface or the coil is actually stationary while the magnetic flux that is linking to it actually changes. How could it be possible? Well, in the coil and the magnet experiment, you place the coil, do not move the coil, but you take the magnet and move it up and down, right. So, when you move the magnetic field, when the magnetic field recedes, there will be decrease in the magnetic field causing a current, and when the magnet approaches the coil, there will be increase in the magnetic field, again causing a current, right. So that depends on what velocity the magnet is actually moving. As I said, there are two aspects to this one, right. I keep the magnetic field as it is, right. I won't change the magnetic field, but I will let the coil move around, right. So let the coil move into the magnetic field and out of the magnetic field. There will be again an EMF induced, okay. Will this EMF be the same as the EMF induced in the other case? Is this also called Faraday's law? Interesting questions to think about, okay. We will talk about that second situation slightly later, okay. So for us, we can substitute for now what is the magnetic flux, okay, and then say what is the EMF. Of course, EMF also can be expressed in terms of the electric field, correct. EMF is integral over the closed loop or whatever the loop that you are considering, E dot dl, that is the EMF over the closed loop, and this must be equal to minus del B by del T dot ds integral over the surface S, which is bounded by this closed curve C, okay. So this is your Faraday's law in vector notation. You have a line integral, okay, of the electric field, and that line integral of the electric field which forms the EMF must be equal to the time rate of magnetic flux that is changing with the circuit, okay. So before we discuss other aspects of this, let us look at some examples of Faraday's law, okay. Let us understand what directions to choose and what we need to do with this one, okay. So as a simple example, first let us consider the case of a loop, okay. Sorry, my loop is not very nicely written, so let me just write down the loop like this. I have this loop with the gap being very small, okay, and there is a magnetic field which is uniformly perpendicular to the loop, okay, has a value of B which is given by some B0 e to the power minus alpha t, okay. Thus the magnetic field associated with this loop is actually in the z direction perpendicular to the loop. So if this is my loop, then the magnetic field is in this direction and it is actually decreasing with time, okay. So this is the magnetic field. Now what is the EMF that is induced? If I take this as my specified direction for the EMF, okay, what would be the EMF that is induced, okay. Now before we actually look at this one, let us look at a voltage source. The conventional form of writing a voltage source is that a current leaves voltage source, the positive terminal of the voltage source, correct. So the current actually leaves the positive terminal of the voltage source, and if we have chosen in the induced voltage in this way, then there must be a current that is leaving here. Remember, this current is not the current that is present in the coil, that is in the sense that it is not initially present, it is the one that is because of the magnetic field that is changing. So I will write this one as some IIND to indicate that this is the induced current, okay, and we want to find whether the induced current will be clockwise in the same direction or it would be anti-clockwise. If it is anti-clockwise, then the terminals for induced voltage would also have to change, correct. So this is what we want to find out. Now before you can do that one, here is a point, here is a typical idea to remember. Let us assume a certain polarity for the surface, right. So this is an open surface, the surface normal can actually point upwards or downwards. If we allow the surface element normal to point in a direction, okay, such that if I curl around my fingers using the right hand rule, the thumb should point along the B region, I mean B fields, right. So if this is the convention that we have been following, right. So if I have the current in the loop, then the thumb points in the B direction and the loop surface area normal also now points in the direction of B field, right. So my B field actually points in the direction of Z, therefore the surface normal also points in the direction of Z, and this would have been the magnetic field that is generated provided there was a current I in the loop, correct. There is current I in the loop, that current would have generated a magnetic field along Z direction, okay. If my induced current is in the same direction as that of the current I marked in blue here, it would generate more magnetic field, right? It would keep on generating more magnetic field and the EMF would actually keep on increasing. So before you solve Faraday's law problem, I would suggest you make these simple pointers. Okay, you establish the surface normal in such a way that the normal should point in the direction of B field, and then establish the direction of the current I that would actually give you the magnetic field in the applied direction. Okay, in any case you have to only note two things: either your magnetic field is in this way or the magnetic field is in the other way, right, in the opposite direction. Okay. Now apply Faraday's law. EMF induced must be minus d psi by dt, correct? And if you assume that the magnetic field B is uniform through the surface and the surface actually has a cross sectional area of S or the cross section area of S, then this can be written as minus S dB by dt. Okay, and EMF of course is a scalar quantity, so there is no vector out there, so you can just take the magnitude of the B and then integrate this, or rather the part of the B and then integrate this one, removing the vector part to this. So if I do dB by dt, what do I get? I get minus alpha into B0 e power minus alpha t. There is already a minus alpha, so that will cancel with each other. I get alpha S B0 e to the power minus alpha t. This is the EMF that I am actually getting. Now with this EMF, what should be the direction of the current? If I take the direction of the current to be along I, terminals for the induced voltage, that would have been reversed, correct? If I take the current, induced current along the same direction, and this induced current would leave the positive terminal, then the induced voltage would have been in this polarity. The bottom one would actually have the plus sign and the upper part of the conductor would have the minus sign, and the induced current would have been in this direction. However, I know that induced current cannot be in this direction. Why? Because if the induced current is in the same direction as I, then the total magnetic field will actually add, and that is what we do not want. Okay. So the induced current is not in the direction of I, rather the induced current is actually in the direction opposite to I, okay, so that the magnetic field produced would actually be going negative, and therefore the total magnetic field would be reduced. So the induced voltage will be positive with the upper terminal as plus and the lower terminal as minus. Okay. So this is what you would obtain from EMF, although we should realize that these are not really critical, because in most cases the magnetic field changes happen in such a way that the EMF would be positive and negative. It is essentially AC fields that would be applied, and therefore the polarity of the induced voltage keeps changing, okay, from plus to minus, minus to plus and minus to plus. So there is really no point in worrying too much about which direction the induced voltage is there, unless there is a very specific reason for this. When we discussed diamagnets, we talked about, in the module of diamagnets, we talked about the induced magnetic moment that would be opposing the B field. There we had to be careful in writing down what is the direction of the magnetic moment. Okay, so here we don't really have to be that careful. However, whatever we discussed for diamagnets, the justification for magnetic moment actually comes from Faraday's law and Lenz's law. Okay. With this, let us consider second example. Okay. This example is the mirror example of the first example. The reason I am putting this down is to just indicate which direction the current would be induced. Okay. So again I have a loop. Okay. These loops are increasingly not becoming circular, but imagine that this is actually a circular loop, and then the magnetic field is still again in uniform along the z direction, and it is given by z hat B0, but this time I am going to change the sign and say e to the power kt. So it is exponentially increasing magnetic field. Okay. So what would be the EMF induced? Again the magnetic field would be generated provided the current I will be in the anti-clockwise direction, correct. The surface area normal will also be along the z direction for this assumption, right, and find out what the induced voltage is. So if this current would have been present in the loop, the current would have actually generated the magnetic field along z direction. The normal to the surface is also along the z direction, but EMF when you calculate turns out to be minus k B0s e to the power kt, right. So, the EMF is turning out to be negative. What does it mean? It means that now if you look at the current direction and if you assume the current direction to be clockwise, then it would be generating the magnetic field in the negative direction, but my EMF would also be negative, right. So, because of that the induced current must be in the same direction as this one, right. So, if the induced current is in the same direction, then it will generate a positive magnetic field, so that the overall EMF would actually be reduced. So, what would happen to the signs of the induced voltage? That would be minus plus V induced voltage. Okay. So, in the previous case dB by dt was negative and in this case dB by dt is positive. So, the sign conventions or the current directions for these two would actually change. Okay. So, that is what we have. As a third example, consider an alternating field applied. Okay. In this we are going to apply a magnetic field of z hat B0 sin omega t. Okay. So, during the first half at least the magnetic field is actually increasing, which means that dB by dt will be, in this particular case dB by dt will actually be cos omega t, and cos omega t is decreasing but it is still positive, right. So, during this half cos omega t is decreasing but this is actually positive, and what would be the EMF induced? EMF induced will be minus omega. So, dB by dt is actually omega cos omega t. So, it would be minus omega cross sectional area S B0 cos omega t. Okay. So, again the induced current directions must be in such a way that initially it would be along I in the counterclockwise direction, so that the EMF is reduced. Now, when in the second half of the region where dB by dt actually goes down, the current direction should actually be in the counterclockwise direction. Okay. As you can see, the polarity of the EMF would actually be alternating from plus minus to minus plus. Okay. As another example, okay, consider a inhomogeneous magnetic field. Okay. Let us assume that B field is given by some Z directed field, okay, except that this would be changing with distance. Okay. So, cos pi r by 2b cos omega t. Okay. However, as far as the right hand side of Faraday's law is concerned, I am only interested in minus dB by dt, right, and this minus dB by dt, assuming uniform cross section for the loop, will be given by minus omega sin omega t, right. And there is also the other part of B0 cos of pi r by 2b in here, correct. Now, what is the EMF produced? EMF produced is integral of this minus dB by dt over the surface, right. What is the surface? The surface integral will be the dr d phi surface integral, right. ds will be equal to r dr d phi. Integration over d phi gives you 2 pi, integration over r should give you a different value. So, it would actually be cos of pi r by 2b r dr integral from 0 to a, if a is the radius of the loop or b is the radius of the loop, let us take. So, this would actually be equal to from 2 pi sin omega t, and there is some 4b square by pi square pi by 2 minus 1, or if you take a is equal to 1 in this particular case. So, if you do all this calculation, you will see that the EMF is actually given by some omega 8 b square divided by pi by 2 minus 1, and in terms of b this would be b sin omega t, because the differential of cos is sine. Okay. So, this is the EMF that is induced. What is interesting in this is that, except that this was an exercise for finding the flux of a non-homogeneous magnetic field, what is interesting is that if we turn off the time variation of the magnetic field and we replace this cos omega t by a constant value, there will be still no magnetic flux link that is changing with time, and hence there will not be any current induced, correct. There will not be any current induced. The current will only be induced only when the magnetic field is changing, and that magnetic field must be changing with time. It can be for homogeneous field or inhomogeneous field, does not matter, Okay. As long as time variation is there, only then there will be current induced. Okay. Again the current direction will be different. For the first half the current direction will be in one counterclockwise or counterclockwise, and for the other one it would be clockwise direction. Okay. So this change would be happening depending on what your sign for dB by dt is. Okay. So if you are given the values of B and omega, you can actually find out what will be the total EMF that is induced. But the point here is that homogeneous field or inhomogeneous field, both will give you induced currents as long as they are changing with time.